Hello, everyone. So, my name is Adrian Torres, and today we're going to be talking about asymmetric Kumada cross coupling reactions. So, when we begin to discuss the Kumada coupling reaction, the purpose of the reaction is to use Grignard reagents and a nickel catalyst. Carbon-carbon bond formation will occur to produce asymmetric products. The main mechanism that is used or observed in this reaction is a stereoinverted SN2-like oxidative addition that occurs with the nickel complex. Posted below in the center is a generic reaction scheme for the Kumada coupling. So it starts with the organohalide, then we react it with an organomagnesium species, and listed as a palladium or a nickel ligand, there are different kinds of transition metals that apply to this coupling reaction. So when they all react, you will get a coupled product. So the first article that I found was nickel catalyzed asymmetric Kumada cross coupling of symmetric cyclic sulfates. The objective of this article was to come up with a strategy for asymmetric Kumada coupling involving non-activated alkyl electrophiles in enantioselective coupling reactions. After reviewing the article, um, on the table to the right in the gray, there's the generalized reaction scheme for the article's reaction. So we see that we have that cyclic sulfite, which acts as the non activated alkyl electrophile. And then we have the aromatic Grignard, which would be the nucleophile in this reaction. They react it with the nickel acetyl catalyst and a ligand. So pretty much the table describes how when you change the ligand or the aryl groups in the reaction, the enantiomeric yield for those changes will be affected. The substrates that were tolerated in this reaction were benzyl groups, alkylated aromatics, esterified aromatics, fluorinated aromatics, sialated aromatics, and cyclic amines. Um, in the table provided, we see that there's pretty good enantiomeric yields for the varying functional groups that were done for this reaction. Um, as far as application goes for this reaction, there wasn't a set application. Future work involves applying the catalyst to other chiral auxiliaries. So moving on to the next article, cobalt bisoxazolene catalyzed asymmetric Kumada cross coupling of racemic alpha bromoesters with aryl Grignard reagents. The objective of this article was enantioselective arylation of alpha bromoesters catalyzed by a cobalt bisoxazolene complex. So as we see in the Kumada cross coupling, not only nickel applies, there are many kinds of transition metals that apply for this kind of cross coupling. So after reviewing this article, to the right we have the reaction scheme. The nucleophile here will be the aryl magnesium bromide, and our chiral auxiliary is the phenyl 2 bromopropanoate. That's going to be that alpha bromo ester. Um, in the table provided, nucleophile variations affect the enantiomeric yield. Talking a bit about what kind of functional groups are tolerated. In this reaction, they had cyclic thiols, cyclic amines, cyclic esters, and alkyl aromatics. On the table to the right, we see similar results to last time. There are very good enantiomeric yields for this reaction. Um, Important to point out that the Kumada cross coupling has various transition metals that work. Initially, it was only nickel, but now we see that there are cobalt and even palladium catalysts that apply. So, application of this synthesis involves the synthesis of pharmaceuticals. So, the article pointed out that they were able to synthesize F phenoprofen and S artemirone, two different medicines. Moving on to the last article, nickel bis oxazoline catalyzed asymmetric Kumada reactions of alkyl electrophiles, cross couplings of racemic R bromoketones. This one has a very similar layout to the last article. The objective is to use the nickel bis oxazoline catalysts used to cross couple alpha bromoketones with aryl Grignard reagents. So let's dive into some of the data. So as always, the table provided on the right describes the reaction done in the synthesis. The electrophile is going to be the aryl magnesium halide. And then our chiral auxiliary is going to be that alpha bromoketone. Um, the table describes the variation of the aryl groups used on the electrophile. Um, the substrates tolerated in this reaction were benzyl groups, alkylated aromatics, esterified aromatics, fluorinated aromatics, sialated aromatics, and cyclic amines. This synthesis showed good enantiomeric excesses and pretty solid percent yields. The catalyst used in this reaction was a nickel dichloride complex. Application of this synthesis was for the expansion of the available Kumada coupling reactions. So just kind of trying to diversify the known reactions for this style of cross coupling. After reviewing these three articles, hopefully I was able to convey that this metal mediated reaction is able to do carbon carbon bond formation using those metal catalysts. Um, there are such a range of applications that can be done using this kind of reactions, some of which, like we saw, were for medicinal purposes. Um, I think metal mediated reactions are pretty cool. Thank you for watching, guys.